Alright guys, welcome back to Algos Made Simple. Got a little bit more difficult of a problem here today, but of course we're going to make it as simple as possible. Try to get us a nice flowing process on this one that we can recall and work back through if we encounter something like this in an interview or just whatever the situation may be. So without further ado, let's dive right into it. Leetcode 133 Clone Graph. Given a reference of a node in a connected undirected graph, return a deep copy clone of the graph. Each node in the graph contains a value int and a list the index node of its neighbors. So I would let the interviewer know, okay, I understand that I'm going to be given a node that's coming from a graph and I want to make a copy of that node and I want to copy all the nodes that come through of that graph and I want to make direct copies of it that contain the same components, the value int, and they're also going to have the neighbor property that has the neighbors. So to be able to do that, the first thing that's going off in my head, this class node that they're going to give us to use, I know I'll probably be using that to make the clones as well because I want them to have the same properties. So I'll utilize that class node and then I'll just kind of insert the properties from there. Conceptually, not that difficult to figure out what you're doing here. As you can see in the example, this is an original graph. These are the connections it has. You can't just return that graph. That's not copies of the graph. It's not a copy of the graph. And if you return it and their copies are in the exact same edges or same connections, that's what you're looking for. But if you return it and they don't have the same connections, even though they're copies, that's not what we're looking for. So again, it's got to be an exact replica, but it has to be copies. An exact replica is not the exact same thing. It's a copy of the thing. So with that being said, again, easy to understand conceptually, a little bit hard to figure out how we want to code it. So that's where going to this game plan is so important, and I would take the time every time, especially on a more difficult problem, to type this out on the Google Doc or whatever you're utilizing, or write it down on the whiteboard. One, it gives you a place to outline how you would attack this problem. If you get stuck, you can go back to your game plan and look up and say, have I used this yet? It also gets your ideas out there and gets you talking and shows the interviewer, okay, this is how they problem solve. They know about this, they know what this is called, what they're wanting to utilize, and if we do get tripped up, then at least that gives some credit up there, like, hey, we knew how to do it, we just lost it at some point along the way or whatever. But having this game plan and this outline should help you from losing it and from getting stuck. It should bring you back stuff that you can kind of grab from as you're coding this problem. So with that being said, on the game plan here, we know we're cloning these nodes, and we know we're going to have to pull them from somewhere. So basically, let's have our own graph here. Let's do clone graph, clone G, and set it equal to a dictionary or a hash map. So we know we're going to utilize that. We know that we are going to go through this graph, or we know it's a graph problem. So most likely we're going to utilize BFS or DFS, especially when you're talking about neighbors. So we either use iterative DFS, recursive DFS, or BFS. I think on a more complex problem like this, and the way this problem's set up, it's better to do BFS on this one just because you can keep everything in front of you and see what all's going on, as opposed to trying to incorporate, calling the function within a function, which is not bad and not a bad way to do it if you're comfortable with it, and something we may utilize for future problems. But here I'd like to use BFS. So you've settled on using BFS. So you put that in your game plan. Well, what does BFS utilize? A queue. So you put that in there. What can you do with a queue? You can pop stuff and append stuff from a queue. So you're probably doing that. The queue, the length of it, while there's something on this queue, if you've done a BFS or DFS before, while there's something on the queue, the problem's going to keep going. So a queue is most likely going to be fueling your loop. So your while loop or whatever loop you're using, the queue will probably be fueling it if there's stuff on it. That's what's going to keep the problem kind of going and keep you working on it. You know that in addition to cloning that initial node, you want to have the clone of the neighbors get attached to it and get appended to it in its neighbor list. So you're going to traverse through the neighbors. So if you haven't done that yet, if you haven't utilized the neighbors, you want to put them in there. And of course, they'll be the ones that get appended to this queue and keep the problem going. So we've got a pretty good idea of what we're going to utilize here. We know also that they give us a class of node, so we're probably going to utilize class node, at least the properties, if not just the class itself, calling the class. So what can we do here? The very first thing you start off with all these problems on these node type problems and graph type problems, if not node. So if you get something passed through that just doesn't have anything associated with it, then what we want to do is just return none. The graph's empty. That's great. We return none. That's the copy. There's nothing to do, nothing to copy. If there's not, we know in our game plan we need our own graph here. So we got cloned G, and again set it equal to empty dictionary, empty hash table, however you want to say it. And then, okay, we've got that empty. Is there something we could put into it? Yeah, we're passing through this node right now. Let's go ahead and make the copy of that node. So how we would do that is clone G at index node. So again, we'll be able to pull the copy here. Is going to be equal to class node, and you're going to have node.val, and you can't just take that neighbor list and put it in there. It's not going to be formatted the same way. It's not being a direct copy. You need to, just for now, have an empty list associated with it, and then we'll append the neighbors to it later on. So you've got your first copy done. You know the neighbors are still left to copy. What is going to fuel you to get to the neighbors? What's going to fuel you to go through the rest of these nodes or whatever on the graph and copy them? Well, we know we said in our game plan we're going to utilize a queue because we're utilizing BFS. So here we go. You could do the DQ in Python or whatever, but we're going to just utilize a simple array. And of course, a queue is no good if there's nothing in it. What can we put in it? Well, there's really only one thing right now, the node. So the queue has the node in it. All right, again, we said the queue will most likely fuel our loop. So that seems to be the next stage here. We're not going to start going through the neighbors yet at this node, because then how are we going to do it for the rest of them? We need to have that where it's looping and occurring more than once for however many there are. So we'll say while queue, and that'll keep us going while there's something in this queue. And we've got that now, so we got it fueling it. We know we can append or pop off of queues. Well, it seems like there's nothing to append just yet. It's probably time to pop something off. So let's go current, so cur equals queue.pop at index 0, and that's going to pull the one on the most left, so first in, first out. And then we'll say, after that, it's time to look at the neighbors. We've got access to that node from the queue, so now we want to use that neighbor property. So what we'll do is for neighbor in cur.neighbors, that's going to allow us to traverse every neighbor one at a time and do some operations on them. What we want to do from there is, if this neighbor is not in the clone graph already, because if it's already in the clone graph, there's no reason for us to clone it. This is where the cloning is going to be happening. Just like when you're using a visited and a different kind of BFS or DFS problem, this is kind of like what your visited thing is, the clone graph. Is it in there? Okay, if it's not, what we're going to do is we're going to do the exact same thing that we did up here. We're going to say cloned graph, but this time at index neighbor, so we're cloning the neighbor, and of course that's going to be equal to the node class, and we're going to say neighbor, and we're going to utilize the value property. And again, we don't want to just take that neighbor list. We want to go ahead and have it where it's empty, or we can append the neighbors to it later on, whatever neighbors it has. So we go like that, exact same format up top. And then what do we have to do? We got to keep this queue going, because now we got a neighbor in here, and we're going to want to search its neighbors and clone its neighbors. So we'll go queue. Again, we haven't appended to a queue yet, so now is probably the time to append. Queue.append neighbor. And once we exit this for loop, that's what's going to keep the problem going, is what we have in this queue and the fact that we have some in this queue. So after that, what do we need to do? Okay, so you're staying in the moment in this problem. We have our node copied, but we haven't copied its neighbors, even though we have the neighbors now. So what are we going to do coming out of this, and staying in this loop, but coming out of this if statement? Whether you win in the if statement or not, we need to put this as one of the neighbors. So we'll go clone graph, and we'll say current, at index current, and you're going to say dot neighbors dot append, and we'll just say cloned at index neighbor. Clone graph at index neighbor. And that is going to take, of course, this right here, which I'll get an error right here with what we got. Anyway, that's going to take this right here, and that's going to append it to your current and their neighbor list. So that'll give you the exact copy we're looking for. Once we've done that, we'll come out here, out of the while loop. Once we've exited the while loop, all we have to do is just return clone graph at index node. And this is happening, I believe, in O of n. It should work flawlessly. You should get your copies of each one. And that's all there is to it, guys. It's just the main thing with these kind of problems with BFS or DFS is to let the problem snowball off itself. So you know you're down here. We've checked and seen if it's not a node, if there's nothing in it, we've returned none. Okay, well, if there is something in it and we're cloning it, we're going to need some place to clone it to. Check, we got that. Do we have something we can clone? Okay, yeah, we got that. We got a node. We can already go ahead and clone that. All right, well, we're going to need to clone other stuff. How are we going to know how much stuff there is to clone? Well, that's where your queue comes in. You know you're doing BFS, that's where queue comes in. You put something in the queue. Okay, we've got something in the queue, now what? Well, we utilize that queue as fuel for the loop. All right, while there's still something going on. Okay, well, now we're coming in here with the queue. What is the first thing we're going to do? Well, we've got something in the queue. We don't want to keep it on there forever. We'll get stuck in this while loop, and we also need to utilize it. Let's pop something off the queue. All right, now that we've popped something off the queue, we've already copied that thing we popped off the queue. We need to get its neighbors. So that gets you your neighbor list. Well, what if the neighbor, okay, so I'm going through here in this neighbor list. What if somebody's got a similar neighbor or the same neighbor, whatever? I don't want to just keep copying clones, and that's not going to give me the same graph. Well, I need to check right here if the neighbor is not in the clone graph. If it's not, then I can do the operations where I'm cloning this neighbor. If it is, I'm going to skip down and just put it as a neighbor for the node I'm working on. But again, if it's not, then I'll come here and I will put it through here and clone it, but I also will append it so I can get the neighbor of its neighbors, because I haven't worked on it before. And that's all there is to it. Go through all that, and then you're just returning the clone to index node, and that will give us the copy of the graph. So it seems a little complex, but the more you do of these BFS, DFS, you'll see they normally build off each other. They're normally similar, depending on what you're working with. They're all kind of similar format to an extent. So just let the problem snowball off of each other. Keep working, keep working. Have a game plan, have an outline. Don't just try to start going here and start coding and trying to say, okay, what do I need next? What do I need next? You've got something to reference of what you need next up here because you made your game plan. So again, guys, thanks for watching. If this helps you out at all, please like and subscribe. If you've got a better way of doing this that you think is simpler and easier to utilize for interviews, please let me know because I would love to utilize it, and I'm sure others would too. Thanks again for watching, guys, and I'll see you in the next one.